Alright, we're going to start to move into a new topic. Now, we've spoken a little bit about gravity, the force of gravity, talking about Fg equals mg. What we're going to do is we're going to do a little bit of an extension on that, just because Fg equals mg is a bit of a limited equation, so we want to expand on that a little bit more. So for the next little bit, we're going to be talking about the force of gravity once again. We're going to talk about Newton's law of universal gravitation, and we're also going to talk about gravitational fields. So we're going to get started on this right away. And the first thing I'm going to do is I'm going to make a really bold claim, and I'm going to say that I am attracted to all of you, and you are also all attracted to me. But before we take that very much out of context, I'm stating that from a strictly physics point of view. I'm not stating that from a societal point of view or anything like that. This is a strictly physics point. And I can stand by that statement with 100% confidence thanks to the work of Sir Isaac Newton. So one of his greatest achievements was to kind of figure out what caused objects to fall near Earth's surface. And that's where you kind of get that whole famous apple story. Or in this case, in this comic, we have a little bit of a revision. We have Newton's falling on an apple. So Newton figured out that the reason that things will fall near the surface of the Earth is due to this force of gravity. So this force of gravity, or gravitational force, which we've called Fg, it is that force that will attract any two objects that have mass. It doesn't matter the mass. We could talk about planets, we could talk about people, we could talk about, subatomic particles. There will be a gravitational attraction. Now, in the case of like subatomic particles or, people, that gravitational attraction is going to be quite small and not really noticeable. When we start to talk about planets and celestial bodies, that one is significantly more noticeable. Now, when we've also talked about force of gravity, we also referred to it as weight. Weight's a bit of a special case. Weight is looking at the force of gravity between an object and an Earth. So it's kind of like a special case of force due to gravity. Now, in our world, or our universe, we've talked about four fundamental forces. Or at least they were mentioned. We talked about the gravitational force, the electromagnetic force, strong nuclear, and weak nuclear. So out of those four, the force due to gravity is actually the weakest of the four fundamental forces. And people might think, well, wait a minute, if it's so weak, like how come I notice the effects due to the force of gravity every day? Good question. The reason for that is because you are on a planet that has a significantly large mass. Earth's mass is about 5.98 times 10 to the 24 kilograms. It will produce a sizable gravitational field. You as a human being with a mass on the order of like maybe 10 to the 2-ish kilograms, somewhere in there, you're not going to have a significantly strong gravitational field. So we're not going to notice attractions that you have on other objects, but with an object such as the Earth, you're going to notice that. So it is actually the weakest of the four forces, even though we do notice it every day because, again, due to the massive object that we live on. The force of gravity is also special in that it's strictly an attractive force. All it can do is bring objects together. It cannot repel them away from one another. Now, the one last thing I just want to mention on this force due to gravity, keep in mind that it does act in a Newton's third law pairing. We experience the force due to gravity because of the Earth every day. Like right now, I'm sitting down on a chair, and we're all being pulled towards the Earth due to the force of gravity. But at the same time, by Newton's third law, if the Earth is pulling down on me, I'm pulling up on the Earth with equal magnitude of force in opposite direction. Now, because I have a small mass, Earth's force on me is going to be very noticeable. My force on the Earth, because the Earth has such a huge mass, it's not going to be noticed at all. But the force that the Earth supplies on me and that I supply on the Earth, they are equal in magnitude by Newton's third law. So the big trap here is people think, well, the Earth's bigger, it applies a bigger force. Nope, that is not correct at all. So be careful with that one. Now, we also talked about this concept of action at a distance forces. So these are forces where there is no physical contact between the objects to exert its influence, and gravity is an excellent example of that. So if you jump up in the air, you may not be in physical contact with the Earth, but the Earth will pull you back down to the ground due to the force of gravity. So this whole action at a distance forces, these have to be explained. And for the longest time, the great thinkers thought that the world was permeated with sort of this invisible jelly or fluid called the effluvium. So if you created a disturbance in one place, that disturbance would propagate through the effluvium and end up somewhere else. Nowadays we know that's a little bit nuts, but keep in mind this was a prevailing theory for a long time. So what we do now is, to explain our observations, is we introduce this concept of a field. So for us, a field, we're just going to call it a three-dimensional region of influence where these action at a distance forces can do their thing. So for us, in a gravitational field, we're going to say that's where the force of gravity can act on objects. In high school, the three fields that you will learn are the gravitational fields in Physics 20, which is what we're doing now. And then in Physics 30, you'll talk about magnetic fields and electric fields. But you'll see those a little bit later. The one thing that I do want to note, and it's really important, a field is not a real thing in the sense you can't go outside and look and see like, oh, there's the gravitational field there. Oh, it's over there. A field is a model. It's a mathematical construct of our observations. So scientists over the years have observed, objects moving under the influence of the force due to gravity, and have taken those observations and put them in a mathematical form, which we call field theory. So those mathematical formulas based on our observations, that's where we're getting this field from, or that's where this notion of the field comes from. It's basically a way of describing our observations using mathematics. Now, somebody might ask, well, the theory we have now, can it change later? Absolutely. If we get evidence that says our field theory needs to be adjusted or refined, that's the whole purpose of science. We've got to keep an open mind. If our theory needs updating, we must update it accordingly. We always want to follow the evidence to see where it leads us. So every object that has mass, regardless of how small or how large it is, it will exert a gravitational force. And then that region where this gravitational force can act, that's what we call this gravitational field. So you can kind of see up here we have the Earth, we have the Moon. So the big thing you'll notice is first of all the arrows for the Earth are longer and there's way more of them compared to that with the Moon. What that's telling us is that the gravitational field of the Earth is considerably stronger. Makes sense. Earth is also quite a bit larger. The key object we want to do, or sometimes when we want to look for a field, we always have what we call a test object to kind of see if the field is there. Because we can't physically observe the field itself, but we can observe its effect on objects. So to test for a gravitational field, we just use some kind of test mass. So for example, this pen I'm holding right now, this acts as a test mass. I let it go, it falls down towards the page, it falls down towards the ground. That's telling me that there's a presence of a gravitational field. It's not a fancy test, but it does show that we do have a force of gravity acting in this region. So we can use any object that has mass to be our test mass. You'll also notice that the direction of the gravitational field, it's pointing towards the center of the Earth, or the center of the object producing the field. That is great. If you'd like to keep that a little bit more simple, we can always use down for our direction. So for Earth, we could say the gravitational field strength is 9.81 meters per second squared down. You don't have to say towards the center of the object. If you want to, that's fine, but as I said, down works perfectly well for this stuff. So based on what we know so far, that little g that we've called the acceleration due to gravity in the dynamics and kinematics, its formal name is actually the gravitational field strength. And based on the equation we've had so far, we could define that as the force of gravity divided by the mass. So this mass here, that'll be our test mass, the one that's actually testing for the field. Now, if we release this test mass, we know on Earth it's going to accelerate at 9.81 meters per second squared, at least near the Earth's surface. How that number actually comes to be, because we've never actually shown you where that number comes from. We just said g is 9.81 meters per second squared. Trust us. We'll show you how to calculate that a little bit later. So this shows the gravitational field strength as a function of distance from the center of Earth. So if we're at the center of the Earth, we're at 9.81 meters per second squared. And then as we start to move away from the Earth, you'll notice that the gravitational field strength drops really quickly. And it's actually a relationship that follows what we call this inverse square. So we would say that this gravitational field strength is proportional to 1 over r squared. We'll also talk a little bit later how the force due to gravity is also proportional to 1 over r squared. because we can see up here that G is directly proportional to Fg. So if G is proportional to 1 over r squared and Fg is proportional to G, then we can say Fg is proportional to 1 over r squared. So last thing we just want to touch on is what are the units of gravitational field strength? Now, we have talked about G being in meters per second squared. We have another set of units though. So I know G is just this Fg over m. Well, if I want to find the units of this, and if you ever see in physics a variable with these squared brackets around it, this just tells us we're looking at units. So the units of G are going to be the units of force, which we know is a Newton, and then divided by the units of mass, which is a kilogram. So the units of the gravitational field strength are newtons per kilogram. Now you might say, well, what about meters per second squared? Well, let's look here. I have newtons per kilogram, and I know the definition of the Newton is a kilogram times a meter divided by a second squared. And I divide that by a kilogram. Well, those kilograms go away, and I get meters per second squared. What this is telling us is that a Newton per kilogram and a meters per second squared, they're interchangeable, and we can use those interchangeably in the course. So when we talk about the gravitational field strength on Earth being 9.81 meters per second squared, we could also say it's 9.81 newtons per kilogram. Which units you use doesn't actually matter. They are interchangeable. You just need to know that. But the reason we tend to use newtons per kilogram is we just want to emphasize that that gravitational field strength deals with a force, and we just want to have those units of force in there, the Newton. But like I said, newtons per kilogram, meters per second squared, use what you want to use.